Hello everyone, welcome back to lecture 6 which is on microwave remote sensing. In this particular lecture, we will continue the microwave remote sensing and we will also have a look on the imaging spectroscopy. So, let us continue this course. So, this is the interferometric SAR, right. So, which is commonly known as InSAR. Synthetic aperture radar SAR imaging system with interferometric configuration is known as interferometric SAR or InSAR. So, this InSAR it is very popular. So, here what happens, it allows accurate measurements of the radiation travel path because it is coherent. Measurement of the travel path variation with respect to the satellite position and time of acquisition allowed to generate digital elevation model, and it can also provide centimeter level information related to surface deformation. That is why this particular domain of microwave remote sensing, the InSAR, it is widely used in the surface deformation studies. High resolution digital elevation model or surface change map due to earthquakes, land subsidence, glacial movement, volcanic activity and land use land cover change. These are most common areas. InSAR is widely used in these particular areas. So, here you can see that this has the interferometric configuration. So, here basically you have two sensors which is looking at the same area and they are generating the microwave images, right. So, SAR interferometry needs at least two radar and radar imaging from two different places. So, remember we are having interferometric configuration, that means we are having minimum requirement of two radars, and these two radars must be placed at different location at the same time and they should be looking at the same area. So, this is called interferometric configuration, right. Phase is a measure of how far the wave has traveled. So, whether it is 0, 2 pi, 4 pi, 6 pi. So, that will provide you how far the wave has traveled. In general, the relationship between phase and distance is 2 pi d by lambda. That is, if we have traveled by a wavelength d is equal to 1, then the phase has changed by 2 pi, right. If it is 2, then it will be 4 pi, if it is 3, then it will be 6 pi. Phase information is effectively random noise in a single SAR image because the phase are randomized by all the scattering on the earth surface, right. So, here this is one example of the phase image and how it appears in your screen. However, if we view from another position very close to the first, then the differences in phase tell us about the difference in distance. I would like to take the example of our eyes. Our eyes are two different sensors placed at two different locations, right, and we are looking at one particular object at the same time. Because of that, we are having the depth perception. If you close your eyes for longer duration, because if you close one of your eye temporarily, you may not feel it because our brains are trained in such a way. But if you close one eye for 1 month or 2 months, when your brain loses the memory of depth perception, then with one eye you will not be able to see the depth, right. So, the depth information comes when we view from two different positions, right. So, this is one example. Here you can see that this is the normal baseline, which is the distance between these two satellites, and this is the phase difference and parallel baseline, right. So, this is from here to here, it is parallel baseline and this is the phase difference, right. Then comes the returning radar signal. So, here these two signals are reaching to these two sensors and they are targeting the same area at a time. Then this is the surface. So, image point is at the same location along this arc SAR phase difference is used to point out the exact location. So, this is the phase difference which is used to point out the location of this particular object, and it will be very precise when we are using the interferometric configuration. So, the difference between the two path lengths related to difference in the phase of the received electric fields, right. Interferometry used to generate two products, one is coherence, another one is phase image, right, which is the phase image is nothing but your interferogram, and you might have heard about it, the interferogram, in many other courses. An entire image of the phase information is known as the interferogram. An image of the coherence, that is the correlation between the two images. So, the coherence, the word itself means the correlation, right, how coherent these two are with each other. Coherence near 1 means the phase information is reliable, that means both the images can be used together and the images have high degree of correlation. When coherence is less than or equal to 0.3 means the image have low correlation and most probably they are noisy. In this case, the phase information is probably not useful. Before you are using the interferometric SAR product, you have to check the coherence. If the coherence value is 1 or near to 1, that means images will provide you very good information. If it is equal to or less than 0.3, you are not supposed to use them together for any kind of quantitative analysis. With microwave remote sensing, the radar signal can penetrate vegetation cover and soil surfaces, right. Depth of penetration is significantly affected by the moisture content, the surface roughness and the incident angle. Remember the geometry of the microwave remote sensing. Maximum penetration is in the arid region with longer wavelength signal. So, you remember different wavelength we have used, and we have a designated letters representing the wavelength, right, in microwave remote sensing. So, that is the longer wavelength region that we have to choose, and the maximum depth of penetration we receive in arid region. Why? Because of the water content. So, here you have low water content and you will have the low dielectric constant, right. So, because of that, depth of penetration will be more in such area. So, if this is the surface, if you have longer wavelength region, it will penetrate more. It will be as good as or equal to the wavelength of your microwave energy. Microwave remote sensing products are widely used in geology, hydrology, oceanography and glaciology, right. So, you might have come across many literatures which we are using microwave remote sensing for soil moisture mapping, vegetation mapping, soil temperature, snow cover or snow water equivalent in the glaciology, sea ice mapping, atmospheric temperature profiling, then humidity profiling, precipitation. All these areas are the possible areas of research with microwave remote sensing data. So, these are some of the potential areas where microwave remote sensing is widely used. Now, we will talk about the introduction to imaging spectroscopy, right. So, this is another important topic which we have to understand. So, let us go back to panchromatic, multispectral and hyperspectral remote sensing. And here you remember this slide where broadband is using a very long wavelength range to generate a single image, right. When we talk about multispectral, we have several bands or images generated in this wavelength range, but in between we can have some gaps where there is no measurement, right. When we talk about hyperspectral, the bandwidth is narrow and the measurement is contiguous so there is no gap in between. When we talk about ultraspectral, again the measurement is contiguous and the number of bands are in the order of thousands, right. So, here one thing which we have to understand, that how we are generating this image. So, if it is broadband, we are having one pixel value, second pixel value, third, fourth and fifth. Then we have another set of pixels. This is how we are completing this particular image, right. And when we extract these DN values, we get only one point in this x and y, which is lambda versus reflectance, right. But when we talk about the multispectral, we have several images available in different wavelength range, which is measured in this way. So, we have few points in this particular graph, which can be connected like this, right. But when we talk about hyperspectral, it is contiguous measurement. So, we have our points in this way, so that we are not losing any information in between, which is missing in this particular setup, right. So, here also we have lambda and this is reflectance. We will have further more details here. Data sets will be much more than your hyperspectral, right. So, this will provide you more information about the target, about their chemical composition, internal atomic structure, right. Now, how we are generating this? We can have one instrument which is looking at the ground, and then we are generating one pixel value, right. So, this is acting as a detector. One detector is capturing one pixel value, right, in case of broadband. Now, if we have this kind of setup, this kind of instrument, let us say 5. So, then we will have 5 pixel value. So, these 5 pixel value can be arranged and we are having this 5 pixel image, right. 1, 2, 3, 4 and 5. Now, similarly, when we talk about multispectral, we have 5 bands or minimum 3 bands, right. So, each pixel will have 3 images. So, individually if we refer to any of the image, then they are having one set of value corresponding to each pixel. When we talk about multispectral, we have multiples of value corresponding to each pixel, right. So, this concept explains the advantage of spectral resolution. So, when we talk about the hyperspectral remote sensing or imaging spectroscopy, the spectral resolution is high, right. So, this is representing a particular pixel from this particular image, right. So, when we talk about the spectral signature, the high spectral resolution, that means it will provide you all the information which were missing in multispectral. Let us say these points corresponding to multispectral. So, this is missing, right. So, what is happening here? That is missing, which is available in hyperspectral remote sensing, and corresponding to these absorption feature, we are able to identify the material whether it is X, Y or Z. So, now you just imagine how important to have these measurements, right. All these dots are from different images, right. Now, once we understand this, that every material has its own characteristic absorption feature, maybe a single absorption feature or maybe a set of absorption feature that can be used to identify them in remote sensing products, right. So, then we can consider this spectral signature or particularly this characteristic absorption feature as the fingerprint of this material, right. So, that is very, very important. So, that comes only when you are having the high spectral resolution. So, internal atomic structure and composition are the reason for absorption feature, and troughs are the places where things are happening. Remember, I told you if there is a tree, why it appears to us in green? Because green color is reflected, right. Green color is reflected, but other wavelengths are not reflected compared to this green. So, let us talk about this 400 to 700 nanometer, and we find that it has reflectance in green region, which is higher compared to blue and red. That means, this particular target is not interested in green wavelength, right, but it is interested in red and blue. And further, if we see the spectra of vegetation, right. So, here it is green, red, and then in NIR you have this kind of spectral signature. So, this is comparatively high, but since we are not able to see this particular region, it appears green to us. But if you see this particular wavelength, here basically it is very interesting to note that this particular wavelength is absorbed by the vegetation. That means, these troughs are the places where things are happening, not these, right, because these are simply reflected by the target. So, that is why the characteristic absorption features are helping us to identify them, to identify their chemical composition or their atomic structure, and to better characterize them in the remote sensing products, right. So, distribution of electromagnetic radiation emitted or absorbed by the particular object, it is a function of wavelength, because these are the wavelengths, right. So, this is a function of wavelength, which is very, very important to remember. Now, when we talk about the spectroscopy, spectroscopy is the study of spectral feature which is dependent on the wavelength and the material or object, right. Spectroscopy is often used in physical and analytical chemistry for the identification of substances through the emitted or absorbed spectrum. So, let us take this example. So, this is the target, so which is getting illuminated by our own source of light. Then what will happen? Some amount of energy will be absorbed, some amount of energy will be reflected, some will be transmitted. So, then we can have different setup of instrument. We can put one instrument here to measure what is the transmitted energy. If we put one sensor here to measure how much energy is reflected, right. So, this kind of spectroscopy we can have. So, here in this case we have the reflectance which is measured by this particular sensor, or if it is absorbing it will emit, and this particular goes to your sensor, right. Then it is getting recorded. So, this is the hyperspectral setting. This hyperspectral data will provide you better representation of the target, because you are able to capture all these absorption features, right. So, these absorption feature or set of absorption feature will help you to identify the material. So, the spectroscopy is the study of spectral features which is dependent on the wavelength and the material or object, and directly indirectly we are referring to the chemical composition and the atomic structure. To acquire spectroscopic information over large area, we need sensors, right, and those sensors should have the capability of generating high spectral signatures. So, it has the power of both spectroscopy and imaging. So, you will have the power of both spectroscopy and imaging. So, in this case what will happen? You will be generating the hyperspectral remote sensing images, right. So, that is also known as imaging spectroscopy. With this we will end this lecture. So, today we have learned about the microwave remote sensing and the imaging spectroscopy. We will continue this topic in the next lecture, where we will learn more about the hyperspectral remote sensing. Thank you.